Hey everybody, Mr. Tegmeyer again, here with part 3, the last part of the Introduction to Thermodynamics presentation. And this last part is going to cover insulation, and we're going to go through an example of that, and radiation. We're going to go through a couple of examples of that, so let's get started. But when we talk about insulation, there are a couple of constants that we need to understand. So one is called U value, and U value is called the coefficient of heat conductivity. So, and it's a measure of material's ability to conduct heat. So the higher the U, the greater its ability to conduct heat. And here you see the equation for it. It's P or power, A for area, and delta T, in this case T, capital T, is temperature. So you can see what the units in the metric system are watts per meter squared degrees Celsius. Now in the US customary system, or the US system, the equivalent of watts or power is BTUs, which stands for British Thermal Unit, and it's per time, so it's BTUs per hour. The A would be square feet, and the delta T, or temperature, would be degrees Fahrenheit. Coefficient of heat conductivity. Well, the inverse of coefficient of conductivity is the thermal resistance, or R value. And when you go to Menards or Home Depot and you walk through the section on insulation, or maybe you've helped your dad with a project, insulate the house. The higher the R value, the greater its insulating capability. So R is just the inverse of U, 1 over U. And there you can see the formula. And what we want to consider for insulation, and we're going to take a look at some examples coming up here, something that we call the bulk R value or the total R value. And thermal resistance, think of a series circuit. We just got done with electricity. So when we talk about bulk R value or total R value, it's just the sum of the individual R values. So let's take a look at what we mean on the next slide. So here we have a cross-section of a wall. So you can see the outside of, so this could be your house or a building of any kind. So on the outside, on the right-hand side, you see some brick, and it gives you what the dimensions are, and it says in parentheses R equals 0.8. So that's the R value of the brick. And as we go to the left, we have a 1-inch air gap. The R value for air is 0.17. And then we have some foil. That R value is, or its resistance is 7.2. Pretty darn good. And then finally, we get to some fiberglass. That's the pink stuff in there. That has an R value of 19. So 19 is higher. It's the highest one here, which is good. That's what we want our insulation to do. So it resists any movement of heat. So remember, the higher the R value, the greater its resistance to giving up heat. And then finally, on the inside of that building or house, you have 5/8 inch drywall. That's 5/8 inch thick. And its R value is 0.56. And then down below, you see a 2x6, and that has an R value of 6.88. So let's take a look at the wall cavity itself. So let's draw a line, horizontal line, through the pink part. And think back to our equation, we just really add these up. So we want to find out what the total R value is going horizontally, left to right, through the pink section. So we just add those up. So we have the drywall at 0.56, the fiberglass at 19, the foil at 7.2, the air at 0.17, and then finally the brick at 0.8. When we add all those up, we get 27.7. Now, what is it though at the stud location? So same type of thing. But here I want you to draw a line, a horizontal line from left to right through the stud. So it's going to go through the drywall, through the stud, through the foil, through the airspace, and then finally through the brick, right at the bottom. And again, we're just going to add all those up. 0.56, 6.88, which is the R value of the stud. We do not consider the insulation in this part because we're not going through the insulation. 7.2 for the foil. We go through the air at 0.17, and then finally the brick at 0.8. And when we add those up, we get 15.6. So you can see that the insulation has a greater R value than the stud, which is why you have hollow walls and insulation, and you don't have wood walls, because wood does not provide as much resistance to heat movement as fiberglass. Well, let's take a look at radiation next. So remember back to the second presentation where we talked about three basic parts of thermal energy transfer. And remember what those three parts were. They were convection, conduction, and radiation. So radiation is energy that's transmitted, a lot of times I think of it through space as electromagnetic waves. And probably the most common thing we think of is what you see here. This guy's he's cooking something in his microwave. And literally we use microwave radiation to cook your food. So the way to measure the rate of heat transfer is with Stefan's law. And there you see this big, hairy, nasty equation. The net energy transfer, P, on the left-hand side. And then you see the Greek letter sigma. That's the lowercase sigma. That kind of looks like an O, like a cursive O. That's Stefan's constant. And you can see the number there. It's a pretty small number. And be wary of the units. It's watts per meter squared per Kelvin to the 4th power. A is area. E is emissivity, and that is dependent on the material. And of course T is temperature. In this case, kelvins, and Kelvin matches the temperature scale in Stefan's constant. So you have to keep, you want to make sure that when you use this equation you're using kelvins. So let's look at an example of using this. So you have a Thanksgiving break and you're sitting at home and you're watching TV. Okay? And so it says prior to dressing for school, or maybe you're just kind of hanging out, you're watching the morning weather to decide what clothes to wear. So the room you're in is at 65 degrees. Your skin temperature, which is not the same as your internal temperature, is at 91.4 degrees Fahrenheit. We want to know what the net energy transfer from your body is if you sit there for 15 minutes watching the weather. So a couple things we need to know. Your skin emissivity is 0.9, and the surface area of your skin is 1.3 square meters. So how do we do this? Well, we use that same problem-solving process that we always do. We list our known values, and we know that the area of your skin is 1.3 square meters. We're given the emissivity of your skin at 0.9. Stefan's constant is always Stefan's constant. We're given your bedroom temperature at 65 degrees and your skin temperature. So we can calculate that it's not delta T, but we'll come back to that in a second. And we know that we're talking about a time span of 15 minutes. And again, we want to express that in terms of seconds. How do we take a look at that? So we list all the known values, or I'm sorry, unknown values. We don't know P, and we don't know Q. But we can use Stefan's law. And we also can use Q equals P times delta time. That's just rearranged from an earlier presentation where we said P was equal to Q divided by delta T. It's the same equation, it's just rearranged differently. So one of the first things we want to solve for is that quantity of T2 squared, I'm sorry, not T2 squared, T2 to the fourth minus T1 to the fourth. And when we do that, we get 1.567 times 10 to the ninth. Now, it's important here to know that you have to convert from Fahrenheit to Kelvin. I'm not going to cover that in this slide, but you have to convert from Fahrenheit to Celsius and then Celsius to Kelvin. Or if you know the direct conversion, you can do that. Then we just go ahead and plug our numbers in. We know that Stefan's constant. We know your skin area. We know your emissivity. And we know that quantity, T2 to the fourth minus T1 to the fourth, we end up getting 103.92 watts. But that doesn't tell us everything. We wanted to know the heat, remember? So that was heat per time. That's what we just solved for in step 4. So step 5, we apply our time, which was 900 seconds, and we get 93,500 joules. So you gave up in that 15 minutes 93,500 joules of energy. Sounds like a lot. Boy, are you hot.